welcome to this particular lecture. Now, if you see what we have to do is that I will show it to you how can we design a gas sensor and what are the process flow for designing that particular sensor. Okay. So, let me show it to you on the slide. Suppose I want, let me first show it to you here, if you can come back to the screen. I am holding a sensor. Yeah, suppose I want to fabricate this sensor. Now, I am not interested in understanding the casing, I am interested in understanding what is within the sensor. Okay. So, here we are looking at the video which will help us to understand what is there within this particular sensor. So, let me just show it to you again, if you can go back to the slide. So, what are we were talking about? We are talking about that we have a sensor and sensor has 4 points. So, the first point should be a heater, first 2 points should be heater, right. These are the contacts to the heater, heater contact 1 and 2, right. This is 1 and this 2. Then on this heater there should be some kind of oxide or insulating material. On this insulating material there should be a sensing layer, but for sensing layer there should be again a electrode. So, this one would be our sensing layer, this one and this one would be our 3 and 4, these are electrodes. This is sensing layer, right. This is our substrate. All right. So, I want to design a process flow, to fabricate this particular sensor. The sensing layer should be metal oxide semiconductor. So, I can use zinc oxide, I can use tin oxide, I can use indium oxide, I can use indium tin oxide, I can use tungsten oxide, right, several way of doing it. Okay. So, let us see the process flow. We start with a substrate, which is silicon, then we grow oxide, so this is stage 1, stage 2, stage 3 how we grow oxide? We grow oxide with the help of thermal oxidation. All right. This is our stage 3. Stage 3 what we do? We will deposit a metal. This metal is for our heater. So, I will say nichrome. All right. Let me give some design to this so that we can understand the difference. After this I need to perform a photolithography technique, to fabricate a heater. So, what I will do is the first step after this would be I take a substrate which is already having a metal. How we will deposit nichrome? We deposit this nichrome using thermal evaporation or sputtering. All right. So, we have this metal. On this metal I will spin coat photoresist. What I will do? I will spin coat photoresist. After spin coating photoresist, I will bake this, which is called soft bake. Bake this at 90 degree centigrade for 1 hour. Okay. Next step is, so you let me write down here, this is my photoresist, right. This is my nichrome, this is silicon dioxide, this is silicon dioxide, this is silicon, and on this I will have a mask, and that mask is my bright field mask. You have seen in the lithography section, right, what is the importance of bright field, what is the importance of dark field, right. So, this is my bright field mask, and this photoresist is positive photoresist. Okay. Next step is, I will expose this wafer with UV light. That is why it is called UV lithography, right. Expose this wafer with UV light. After exposing the wafer, I will dip this wafer in photoresist developer. After exposing the wafer, I will dip this wafer in photoresist developer. When I dip this wafer in photoresist developer, what will happen? That the unexposed area will become stronger and the exposed area will become weaker and get developed. Why? Because the positive resist. For the positive PR, the unexposed region becomes stronger, we know that, right. So, this photoresist is here. Now, after this I will do a hard bake, I will perform hard bake. Hard bake is done at 120 for 1 hour. When I perform hard bake, after this I will dip this wafer in nichrome etchant. Nichrome etchant. When I dip this wafer in nichrome etchant, what will happen? The area which is protected by photoresist, will remain, and the area which is not protected by photoresist will get etched. All right. After nichrome etching, next step is I will dip this wafer in acetone. I will dip this wafer in acetone. Why? Because when I dip this wafer in acetone, I will strip off my photoresist. Now, what I have is a sensor or is with a substrate with a micro heater. I have a substrate with micro heater. But what I want? I want a substrate with micro heater. This is your heater context 1 and 2, right, and a sensing layer and electrodes, right. So, once I have a substrate with micro heater, so let me draw it here. All right. This is our silicon dioxide, this is silicon, silicon dioxide, silicon dioxide, this is our nichrome heater. Okay. Now, what we will do? We have to have insulator, because we cannot directly deposit metal oxide semiconductor on the micro heater. So, for having insulator, we have to use PECVD. PECVD. If I use PECVD, what will I have? I will have my heater with an insulating material. So, there will be insulating material on the heater. Okay. This insulating material can be SiO2 or Si3N4, silicon dioxide or silicon nitride. This is my nichrome, this is my silicon dioxide, this is my silicon dioxide. Now, can I directly deposit my semiconducting material on this particular insulating material SiO2 or SiN3N4? No. Why? Because I am not able to access the contact area of the heater. If I draw the top view of this particular slide, my top view will look like I have a heater and everywhere there is a oxide, everywhere there is oxide. So, I cannot hit the heater. For that, what I have to do? For that, I have to open the contact of the heating material. That means that everywhere there can be silicon dioxide except on the heater contact, except 1 and 2, everywhere should be silicon dioxide. So, for that what we need to do? We have to perform again a photolithography, so that we can open the contact or heater contacts, right. We can open the window and we can have the heater contacts. So, let us see how we can do that, all right. So, after this we will have photoresist. So, if I write it down, so you do not get confused, this is my insulating material, let us say silicon dioxide, this is my heater which is nichrome, this is again silicon dioxide which is thermally oxide, this is silicon dioxide again thermal oxidation, this is my silicon which is my substrate, and this is my positive photoresist, right. Now, I will, after positive photoresist, spin coating positive resist, what I will do? I will soft bake, do not forget the steps. Okay. Soft bake is at 90 degree for 1 minute. If I have written somewhere 1 hour, it is not correct, just understand 90 degree 1 minute, 120 degree 1 minute, okay? Not hours, 90 degree 1 minute, 120 degree 1 minute. After this, I will load the mask, and this time my mask should be such that I want this area to be opened. Which area? The contact area of the heater, right. The heater windows, the contact area to the heater windows should be opened. So, this is my mask. What is this mask? This mask is dark field mask, all right. Next step is I will expose this wafer with UV light. After exposing, my next step would be I have to develop the wafer. For developing wafer, we have to use photoresist developer, right. So, if I dip this wafer in photoresist developer, after unloading the mask and after UV exposure, what will I have? I will have my photoresist in the area which was not exposed by UV, and you can see here the windows for the contact to the micro heater are opened. So, what is the next step? Once I have this, my next step is I will go for hard bake. Hard bake is done at 120 degree for 1 minute, correct. Okay. If I go for hard bake, the next step would be I will dip the wafer in BHF. BHF stands for buffer hydrofluoric acid. If I use BHF, what will happen? I will etch the silicon dioxide from the contact region, which is my heater contact. See, there is no silicon dioxide here now. There is no silicon dioxide in this particular area. Now, I can access my heater, right. Now, I can access my heater, but what I should do with this photoresist? I have to strip off the photoresist. So, after BHF, after I rinse it, every step understand that there is a rinsing. Okay. You have to wash the wafer with DI water. You have to rinse the wafer, RINSE, rinse wafer with DI water, DI water. After every step you have to go for rinsing with DI water. Now, after this we need to strip off the photoresist. What we should do? We should dip this wafer in acetone. If I dip this wafer in acetone, my photoresist will be stripped off. If my photoresist is stripped off, then what will I have? I will have a micro heater with silicon dioxide except on the contact pad, right. What is the next step? See, now where are we? If I show it to you here, this is silicon dioxide, right, and this one is silicon dioxide, this is my heater. Now, on the silicon dioxide what I have? I want to have sensing layer and electrodes. So, on this what I will do? I will, after this the next step would be I will deposit a metal. So, let me have pattern for metal as XX. This metal is for, this is chrome gold. This chrome gold is for electrodes. You can see, right, there are two heater contacts. Now, I want to have electrodes. So, for electrodes I will first deposit the metal using thermal evaporation, right. After depositing metal, the next step that I will perform is photolithography. Now, you guys know, right, for photolithography what we need to do? We have to deposit. So, this is my metal, of course, chrome gold, and here is my photoresist, right, positive, soft bake. After photoresist spin coating, we have to have soft bake. Soft bake is at 90 degree 1 minute, followed by loading the mask, and this mask is bright field mask. This mask is bright field mask. After this UV exposure, after UV exposure we have to develop the wafer. When you develop the wafer, what will happen? The photoresist which was not exposed is stronger. The photoresist is this area, and then right. After this, if I etch this wafer, etch chrome and gold by dipping the wafer in chrome etchant. First is gold etchant followed by chrome etchant, because chrome is at the bottom. So, first I will dip this wafer in gold etchant followed by chrome etchant. What will happen? The photoresist, the area which is protected by photoresist will remain as it is, and the area which is not protected by photoresist will get etched. All right. So, area which is protected by photoresist is stronger, area which is not protected by photoresist, right, will get etched. After this I will dip the wafer in acetone. Before that, of course, after developing the photoresist we have to do hard bake, do not forget that. So, after this, if I dip the wafer in acetone, I will strip off my photoresist. If I strip off my photoresist, what will I have? I will have chrome gold electrodes over nichrome heater, and in between there is a insulating material which is SiO2. What is the next step? Next step is I will deposit my sensing layer, which is my metal oxide semiconductor, let us say ZNO sensing layer. All right. How will I deposit my sensing layer? By sputtering. You take a zinc oxide target and then sputter it to form a film of zinc oxide. But do we require film of zinc oxide everywhere? No, we only want film to be on this particular electrode and the contact should be open. So, after this the next step would be spin coat photoresist, perform soft bake, load mask, bright field mask. We only want to protect the photoresist over the electrodes and not on the contact area. So, we only want to protect the zinc oxide only on the electrodes and not on the contact area of the electrodes. So, we have this bright field mask, right. This is zinc oxide is here, all right, and this is our bright field mask. Next step is we will expose with UV, right. After this exposure, if I develop the wafer, what will happen? If I develop the wafer, then I will have my photoresist only in this area, because I used a bright field mask with a positive photoresist, and that is why the unexposed region became stronger. After this I will go for hard bake, 120, 1 minute, and then I will dip this wafer in zinc oxide etchant. I will dip this wafer in zinc oxide etchant. If I dip this wafer in zinc ZNO etchant or ZNO etchant. So, if I dip this wafer in zinc oxide etchant, what will happen? I will have zinc oxide only on this area, right, only on this area. Why? Because this area is protected by the photoresist, correct. Last step is I will dip this wafer in acetone. If I dip the wafer in acetone, what will I have? I will have my silicon oxide, that is oxidized silicon wafer, on which I will have my heater, then I have insulating material, right, on which I will have my electrodes, right, and my heater, right. So, this is my SiO2, this is SiO2, this is SiO2, this is nichrome, this is chrome gold, and this one is my zinc oxide, right. If I dip this particular wafer in acetone, my photoresist will be stripped off and I will have my zinc oxide material on chrome gold, which are the electrodes. So, how many contacts are there? I have 4 contacts, 2 for the electrodes and 2 for the heater. Alright guys. So, this is the process flow for fabricating a sensor. Now, if you see, if I want to heat this particular silicon substrate, then I will require some x amount of power, right, x amount of power. If I want to reduce the power consumption for heating the silicon substrate, I can make a diaphragm. What I can do? I can make a diaphragm. What does that mean? If I etch the silicon substrate with bulk micro machining, right, then now I have to heat, sorry for the design like this, okay. This is a kind of little bit better than earlier one. Okay. Now I have to heat thin layer of silicon, and that is why my power to heat the semiconducting oxide will reduce. So, to obtain 100 degree centigrade or let us say 400 degree centigrade, earlier was let us say 100 milliwatt of power we required. Now, for the same temperature, if you want to reach 400 degree centigrade, I will require less amount of power because of my micro machining. So, this is a separate topic, we do not get into this, but I am just giving an example that you can design a sensor and you can do this micro machining to fabricate the entire gas sensor. Alright guys. So, what we have learned? We have learned this is last slide. So, what we have learned? We have learned how we can design a gas sensor, we have learned how we can fabricate a gas sensor, process flow, and how can we design the signal conditioning circuit that can be attached to a gas sensor, so as to control the heating of the gas sensor. Again, this is a part of where we are understanding the heating of the gas sensor, but what about further changing the resistance to a readable format. So, that we will be looking at or we have looked in the earlier slides, or if not we will be looking in the next slides or next lecture in fact, right. So, I hope that you understood the importance of sensors, in particular you understand how you can design signal conditioning circuit for a particular sensor which is a gas sensor, and how you can fabricate a gas sensor using the process flow that I have shown you in this particular module. Again, to understand the process flow, there are a lot of things that we need to understand. For example, what kind of silicon substrate you have to use, what is the thickness of silicon dioxide, what kind of material you use, and what is the thickness of the sensing material, what is the thickness of electrodes, what is the thickness of heater, which material to be used for heater, why only nichrome, why not platinum, why only chrome gold, why not other material like aluminum, right. Then why zinc oxide, if I change the zinc oxide with tin oxide or indium oxide or indium tin oxide, what will happen, if I use tungsten oxide, what will happen. These are all 2D materials. If I go for like so there is a thin film, right. If I instead of thin film use nanostructures or nano wires, will my sensitivity improve? Lot of questions, right. To give you answer quickly, aluminum cannot be used because it get oxidized, right. Nichrome is easy to fabricate, platinum is costly, chrome gold can be used because you know the conductivity of gold is very good compared to platinum, platinum is costlier, chrome gold is cheaper. Now, if you want to talk about the different materials, each material has its own characteristics for sensing particular VOC, right. When we talked about zinc oxide or indium oxide or tin oxide is extremely sensitive, indium oxide is selective, indium tin oxide we can use both the parameters of indium oxide and tin oxide. So, these are the some of the equations that you need to understand. What is the thickness, what, so this everything about the thickness, changing that heater temperature, everything you can do if you know how to perform a simulation using a software called COMSOL multiphysics. Alright. So, we will see how a COMSOL multiphysics can be utilized to understand and to simulate your sensors in a next module, right. Till then you take care. If any question you ask me, right, or ask in a forum, we will be very happy to help you out. Again you understand this thing, this is all thin film technology where you require sophisticated equipment like clean room, inside the clean room for example thermal evaporator, e-beam evaporator, sputtering, photolithography, wet etching, dry etching, right. But if I want to use screen printing then I can do it anywhere in the with a little bit of facility, because in screen printing what I want, I just want, let us say you have this particular screen, right, you have a screen. Now what I am doing is I am just cutting a sample from that particular screen, alright. One second, just to give you an example, okay, just to give you an example. So you guys understand how, what is the advantage of screen printing and how you can utilize it for in your lab. Now this is a let us say a pattern. What will happen if I load this screen onto a substrate, let us say now I have loaded the screen onto a substrate, right. If I deposit, if I have a material which is my sensing material and if I use a squeezy, right, squeezy is like, understand that there is a sensing material here, if I squeeze it like this on this particular substrate, what will happen, that the material will pass through this particular hole, remaining area will not be affected. So when I remove this mask, I will only have the central region where it will have sensing layer, right. Now if I heat this one at a particular temperature, I have my sensing layer ready. So screen printing is very easy to work on compared to thin film, right, but there are disadvantages, like in thin film you can have an extremely minute sensor, in thick film it is a kind of difficult. Again once you have sensor you need to have a signal conditioning circuit. Alright, so till then you take care, I will see you in the next class.